geometry of mathematics, then it means that you understand that concept. So always try to uh, recall the geometry. So today we will talk about inner product of space. It is more what we say that it is generalization of Euclidean space. Till now we had already seen that Euclidean space. That means whenever something is happening, we always talk about vectors in the form of Euclidean vector. That means one dimensional vector, two dimensional vector, those kind of things. We are not talking in general other than Euclidean space. So generally, if you see things around us, then always those things happens in non-Euclidean kind of things. Like if you say curve is not a, we can't say that it is a line. It is a not line. Line happens to be Euclidean kind of things. But if I say curve, what is curve? Curve is actually it is non-Euclidean things, but deep down inside it can think itself. This curve can think itself as a line. How? So if you convert this, you can write it this curve like this one. What would be? It is a quadratic kind of curve. So you can write the definition of this curve like this way: f of t equal to a naught plus a1 t plus a2 t square. It come directly. It say that it is a curve. It is a nonlinear things with respect to what? With respect to variable t. But if you try to see this curve closely, actually it is linear in with respect to parameter a naught, a1, a2. So that's way it behaves like a what? It behaves like a linear kind of a structure in higher dimensional subspace. Because this curve you are plotting in 2D, it looks a linear, but in different space it can behave like linear. Right now it is non-linear. You can say that it is a non-linear function. You can say that. So this one is a non-linear function in R2 because it is a curve. But I can make it a linear function where in different dimension, in different space. What would be how? So what is the perspective visualization? So always what we do when we define a function f of t, always we call it y, something like that. And the what independent variable we always denote it by x. So you can simply give another notation of this function like this way: y equal to a naught plus a1 times x plus, I'm relating, trying to relate this presentation with your high school calculus what you have already gone through. So that's where you won't face any problem. So generally you are writing a quadratic curve, a general quadratic curve like this way: a naught plus a1x plus a2 x square. Yeah, it is fine. So what you do little bit tricky things here in order to. So right now this curve it looks like a uh, nonlinear structure in R2. Now, how can we convert this one into linear pattern? So we can convert. How? So bring the variable terms left hand side and write it like this way. So you can write it in all these terms like this way. You do one thing here, put it here, bring everything here. So here put it x. Okay, this would be next would be x square, and third would be y. Now try to look from this perspective. What is the coefficient of x? It is a1. Coefficient of x square is a2. And what is the coefficient of y? You have taken y that side, so no worry. Or whether you bring it this side, it won't affect -1 or 1, whatever you want to take. And even simply take it to 1, it won't affect much. I have to stick with this notation whatever I have taken. So I'm taking -1. So I have brought all these right left hand side, so that's where minus is coming here. If you multiply, so I'm writing these things in term of dot product. So dot product of vector, three dimensional vector x, x square y with minus a1 minus a2 1 equal to what it would be. Dot product always it happens what? It happens to be a scalar number equal to a naught. So what you observe? So call this vector x. Call this vector x, or you can call it basis vector x. You are writing it x transpose. Call this vector w, weight vector w, x transpose w equal to a naught. You will see whenever I will discuss about linear regression in next course, that time I will give all the geometric visualization. So what kind of representation you observe here? This one was non-linear representation. Have converted into this. It is a linear representation. Linear with respect to what? Linear with respect to the involved parameter or coefficient. So it is linear in coefficient. So that's where we get a linear picture. So linear algebra is also coming in order to explain nonlinear kind of things as well. So that you need to see the variation where which things vary in linear way. So definitely if something is varying in linear way, definitely linear algebra will come. Here we know that a naught, a1, a2, all these are what? Coefficient. If you change the coefficient, you will get different quadratic function. If you so there would be a family of quadratic function. That means you are talking about variation in parameter or coefficient. So parameter coefficient is having another name parameter. So if you observe variation in parameter, then you got a linear picture in w. Call it in or in weight or in parameter. There are many names: weight, parameter, w. All these are synonymous. And you observe here nonlinearity in variable, independent variable x. The first, so that is the picture, or x or t. Here I have taken independent variable t. Here I have taken independent variable x. So just you might be you might have enough idea of which one is independent and which one is dependent. So I don't have to explain every time, you know, from your high school that. So that is the picture of linear algebra. So linear algebra is coming everywhere, where it is a linear thing or where it is a non-linear thing. Definitely linear algebra will come. There is one more version of linear algebra in differential equation or in dynamical system. What is happening? Things happens in non-linear in nature. So what you do? If you zoom it out, that means you if you apply neighborhood concept there, you try to look in neighborhood. Then what is happening in neighborhood? You get a linear picture. Like if I recall derivative, what is that concept of slope and uh, concept? Just recall the concept of slope and uh, tangent of a curve. So if you take any nonlinear curve, so you come like this way. Suppose this is the curve, nonlinear curve, and at this point call it x naught. X naught is any given point. At this point you are dividing, you are deriving derivative. So derivative would be what? Derivative at this point it will talk about the slope of the tangent. Tangent. This is the tangent line. Call it simply I denote it by t, tangent line, and this is your given function y equal to fx. uh, Y equal to fx is given function, and tangent happens to be what? Tangent line happens to be a line. So you can call it uh, tangent line t of one. I have taken it that it would be a line. Line means it is a linear function. So that's why one is a degree of the linear. What is the degree of linear function? It is one. It is a linear polynomial. So it would be something a naught plus a1 x. And if you try to recall your math one from here, you will come to know what is a naught. A naught is nothing, just it is talking about f of x naught. And what is a1? A1 is nothing, just it is talking about slope. That means it is talking about f dash at point x naught. And what is x? If this variable x, simply here it will actually the point of reference is x naught, because you are dealing with tangent at x naught. So here simply x will not come. In place of x we will have x minus x naught, because here our point of discussion is x naught. So that's why x minus x naught is coming. If point of discussion happens to be 0, then simply it would be x minus. So this tangent line, equation of tangent line is nothing, just it is f of x naught plus f dash at point x naught into x minus x naught. You know the equation of tangent line. Okay, you come across to see, okay, like this pattern. And what is happening, if you try to see, just zoom out this one is the uh, this is neighborhood of what we call, this is neighborhood of x naught, that means it is talking about near about x naught. Then in that perspective, what is the neighborhood of this function? So this box under that means what is the content of the function f under this box. So if you zoom it out this box, this neighborhood, so like this way. So this point is what now, your reference point is now here, this one would be x naught, and the corresponding the y coordinate would be f of x naught. Okay, I'm zooming out this point. Okay, so just zoom like this way, I'm giving a zoom picture. Okay, f of x naught. So here at this point, uh, if you I have zoomed it, so this function, it is a non-linear, but if you zoom, then it will behave like linear. Okay, it is almost linear in this zoom version, and almost linear is matches with the tangent. Tangent is always linear. Tangent at this point is always linear. I had already plot this one, but I could not put that in this slide. Later I will give, if you have any hesitation, or you are having difficulty in understanding this plot, then I will come with that drawn plot. Okay, it is coming like this way. So it is already tangent, and it is the function is almost linear in this zoomed version. Okay, almost linear. So that's why here, with respect derivative, you in this zoom version you always see a linear version of the function. So that means simply apply linear algebra technique here. So this approach we are calling it linearized uh, system. That means what you observe robot. If you try to observe robot is what it is defining this pattern. The robot is a piecewise linear system. Piecewise. If you try to zoom it out, the robot is a linear system. So that is the concept. That concept of robot is based on this linearized version of the nonlinear system. Okay. So coming to today's outline of lecture. First, I would generalize inner product for general kind of linear space other than Euclidean space. Then I will define orthogonality and orthogonal projection concept there in the generalized linear space. That means whenever here I am talking about linear space, I'm talking linear space other than Euclidean space, because Euclidean space you are already familiar with in previous classes. You have seen a lot of Euclidean space. So only few uh, non-Euclidean space we had already seen that. For example, those were polynomial space P2, P3, or Pn kind of things, or Fourier space kind of things, or exponential space kind of things. We had already seen that. So I will talk about those kind of spaces, and we will define inner product in those spaces, and what is the structure of inner product there. It would be what is the geometry of orthogonality and other kind of things we'll discuss. And also I will talk about extension of least square approximation to continuous person. That means here we will talk about that this is the extension of continuous least square is just extension of orthogonal projection. That means if you are having a function f and we are pulling what we do, f is a function, and now f is what, it is coming a vector space which is non-Euclidean vector space. So what we will do, we will try to project f in another basis element. Here basis element would be again function. So we will talk about projection of function. Remember that in previous classes we had discussed about projection of vectors. So here things are changed, we are talking about projection of a function. So a really interesting thing it would be, it is just related to continuous least square approximation. Okay, if time permit, then I will go to discuss about one important application of projection of function is like Fourier analysis or Fourier series. Fourier series is nothing, just it is a projection of a piecewise continuous function to orthogonal kind of function like sine and cosine kind of function. You had already seen that Fourier series of a periodic function or piecewise continuous function always involve what? Sine and cosine. So that means you are projecting a given any kind of function to that collection of sine and cosine. That means basis function happen to be sine and cosine kind of function. So that structure you had already seen in other courses. So those things I will talk about from project orthogonal projection perspective. Okay, so coming to inner product, so first I will give the definition of inner product. And if you are having a linear space which endowed with inner product, then that linear space we will call it inner product space. That means we are having a linear space which is having definitely one inner product. So the, and with respect to that inner product, we can enjoy a lot of benefit. Remember that we are talking about a non-Euclidean space. Euclidean space, there is already a variety of inner products. So we won't discuss that. Uh, we are discussing other than Euclidean space. So inner product space, it is a linear space. It is endowed with a bilinear map. That means it is just consider it is a generalization of dot product. So generalization of inner product, it is defined from V cross V to R, and we denote it generally by uh, inner product of F with G. We denote it by this way for any two element from the linear space B, such that this inner product or this bilinear map, bilinear means it is linear both in F and G. Remember that here we have taken field R, real number, our field, that means entries of the concept are coming from real number. Every entry, whenever I am calling it entry, that means you are talking about very elementary level entry. That means matrices are having entry, vectors are having entries, those kind of things. So here entries, that elementary kind of structure happens to be real number. So from that means a scalar are simply a scalar, whatever a scalar concept you have already seen, that a scalar are coming from real number. So that is the criteria. And the inner product, it satisfies the following property, that it satisfies symmetry. That means order is immaterial. That means whether you do inner product of F with G or G with F, both value are same. It's talking about symmetry. Then again you will talk about inner product is always a linear. It is linearity it is talking about. That means if you take a linear combination of any two element from V, any two element from linear space or vector space from V, and do inner product of G, then it would be equal to the corresponding linear the linear combination of the inner products. So that is the concept of linearity. Again, it also, if you take any non-zero non-zero vector of linear space or any non-zero element of linear space, and if you do inner product with itself, then it would be always greater than zero. This property we are talking about positive definiteness. So inner product of zero with itself would be zero. Okay, and if you are taking a non-zero inner product of any vector with any non-zero so that means f you are, it is a non-zero vector, and you take inner product of f with itself, then definitely that quantity would be greater than zero. Always it would be greater than zero. That is the criteria of positive definiteness. So these three properties always satisfied by inner product, and also this property is also satisfied by dot product as well. So there is no much difference. You can just relate it, or just you can see all these pictures there in the dot product as well. So dot product, that means inner product in Euclidean space. You can give a specific name. That one is dot product. So if you define inner product in inner Euclidean space, then simply you can call it dot product. But if you define inner product in non-Euclidean space, then you simply you can't say dot product. Just call it inner product. So inner product in Euclidean space is a dot product, but inner product in non-Euclidean space is just a Euclidean inner product. So that is the concept. So it is dot product in Euclidean space. That is, what is Euclidean space? We do not generally denote it by Rn. Rn happen. So so that is the concept. So a linear space, that one is having an inner product, is we call it inner product space. For a fix, if we fix taking a fixed element from the linear space or vector space B, and we define a map TG, that means it is assigned by G from B to R through this inner product, then we always say that TG is a linear transformation from where to where, from the given vector space B to R. So it is again a inner product. It is a linear transformation. That's why what I had already told, that inner product is a bilinear. That means whether you define inner product with respect to F or G, it would be a linear in both, linear in F, also linear in G as well. Remember that your entry level scalars are happens to be real scalars. When you take complex scalar, things happens in conjugate way. So I'm not talking about conjugate, complex scalar. Okay, so we see that an inner product space behave like Euclidean space as far as addition, scalar multiplication, and dot product. So that means every non-Euclidean space which is having inner product, those will behave like Euclidean space Rn. So that's why we are defining inner product space. Okay. I've taken few example. Simplest example is coming this one, CAB. It is talking about collection of all continuous function. So it is talking about collection of all continuous function defined from interval closed and bounded interval AB to R. Remember that it is collection of all continuous functions. C refer for continuous. So here it is a function and it's continuous. Every element of that means every element of this linear space you can simply denote it by B equal to CAB. So every element of this vector space or linear space B is continuous function over interval AB. So now we are having interesting thing is that we can say that it is an inner product space. Then if you we are saying inner product space, then you will ask what is the inner product in this vector space or linear space. So inner product we will define it here. Once we have an inner product in a linear space, we can define. So we are it is giving a freedom of defining length, orthogonality, and other related concept that we had already studied in Euclidean space. So if we consider CAB as a collection of all the continuous function defined over the closed and bounded interval AB, where we are taking A is less than B, then what is the inner product over this inner product over this linear space we define like this way. If you take any two continuous function f and g over the interval AB, then inner product we define in terms of integral. So we say that it is integral of this product f and g, integral of f into g over the interval AB. So this is the new definition of inner product in this linear space. So if you ask how it is related with dot product in Euclidean space. So generally, if you take a function is having infinitely many points. When you are taking a vector we are talking about a single point. But when you talk about function is a collection of points which is following a path. So that is the criteria. So that's way. Suppose we have taken this function, just recall Riemann sum in from math 1. So how we convert this integral in term of summation. So this integral can be approximated by this Riemann sum. That means whatever this function integrate function we are having, and what we do discretization of our the given domain. So domain is what? AB. So here it is a starting point, suppose this one A, and ending point is B. So we do discretization of this one. We discretize this interval into n sub interval. So this call it T naught. This one is call it T1, and last point call it Tn. Okay, this B equal to call it Tn. So you have done n partition of the interval. N partition concept just recall from math 1. So this integral you can write as a summation of this. It is what? It is just talking about very elementary. It is giving area, meaning area, bounded area kind of structure. So you can easily visualize from it is just part of Riemann integral. You can say that it is a Riemann sum. So this structure is a Riemann sum where k is varying from where to where. K is varying from 1 to n. That structure is coming here. Okay, and further if you try to look into the in a more zoom version, so what kind of a structure you will observe that it is talking about nothing, just it is talking about dot product of this vector and dimensional vector and this vector. That means in this uh, interval ab you have introduced partition. That means you have divided into n number of sub interval. In n number of sub interval, just you know about those sub interval points T1 up to Tn. Okay, with respect to that, introduce get the value of corresponding functional and do dot product of this one. So it is just dot product of this one, and delta t is what? Delta t is the step size. Okay, then you may ask why we don't observe delta t in case of 2D vector. Suppose we are taking 2D vector in R2. So if we are taking 2D vector in R2, then what would be coordinate of that one? Coordinate of that vector would be A1, A2. And if you take another vector B, then what is the coordinate of that vector in R2? It would be B1 and B2. If you do dot product, what is the dot product of B and A and B? Dot product of A and B, it would be just A1 times B1 into A1 times B1 plus A2 times B2. Then we don't observe here delta T. Why? Delta T is talking about the difference between conjugative indices. So what is the difference of 2 and 1? Difference of 2 minus 1 is what? 2 minus 1 is 1. So 1 is just insignificant. So 1 is not, it just become identity kind of approach. So that's why here delta T here it becomes what? It becomes 1. Difference between conjugative uh, indices. So difference. What is the difference between conjugative indices? It is 1. 2 minus 1 equal to 1. 3 minus even further whatever if it is 3 dimensional, 3 minus 2 it would be 1, and 4 minus 3 it would be 1. So those kind of things are structure coming here. But here delta t, if you take a difference between t2 minus t1, what are the indices here? Ti's are the indices. So difference between t2 minus t1 is what? Delta t. Same uniform step size we had taken. Someone can take a non-uniform, then that would be very much complicated. So simply you can say that delta t is what? It is a uniform step size between tk and tk minus 1. You can say that. That's way in this dot product, in case of function, uh, we are observing delta t as well. So everything I have already explained here regarding inner product in CAB. That means this kind of linear space, a space of all continuous function defined over the interval AB. This is, so you can say that this kind of inner product in non-Euclidean space, it is just generalization of dot product in dot product of the Euclidean space. So it is generalization perspective. You can observe it here. Further, I have also given geometry of that generalization. So if you are in a collection of all continuous function defined over the interval AB, then you can take you can what is meaning of continuity? That means if you want to draw the plot of that function, that means your pen will never you will never stop until terminal point. So like so, that is the meaning of continuity. You are never dropping, just uh, you are starting and ending at the terminal point and ending. That is the meaning of geometrical visualization of continuity of a function. So you can observe that you are having two functions. This function is f continuous function. Clearly it looks from the graph. G is also continuous. So we try to define a dot product. So if you try to define a dot product through this integral, you can easily define. But if you try to visualize from Riemann integration, what you do? Partition the given interval AB into n number of partitions. So this is the partition of the given interval, and with respect to those partition, so at partition point, define the value of function. So this is the value of the function at partition point. This dot, and what you do? Define a dot product, multiply with delta, and that will give an approximate inner product of these two functions. So it is a way of finding inner product of function. function from this way. That means any non-Euclidean factor. Simply function, you can say that it is a non-Euclidean factor, because CAB is also a vector space. So every element of that vector space, you can call it a vector, or in general, it is a linear space. Okay, so it might be clear to everyone. I am taking one more example. So same example I have. Okay, so don't call it CAB. I had already discussed. I'm taking sequential space that we denote it by L2. This L notation we in mathematics we call it L in L notation, or simply I am calling it L2 here. So L2 is the space of all square summable infinite sequence. So it is a sequential space. That means if you are taking any element from L2 or any vector from L2, because L2 is a vector space or linear space, so you are free to call it X a vector. So if you take any vector, then definitely it will have how many entries? It will have infinite entries. And with the property that, so you can say that X is a sequence. What is meaning of sequence? Sequence is always having infinite entry. And then we talk about convergency of sequence. So L2 is a collection of all the sequence, and sequence in such a way, if you do a square of every term and you define a series, then series is always convergent series. Less than infinity, it is always talking about convergent. So L2 is collection of all a square summable infinite series. That means this if you define a series, you are taking a series X and you took a square of series with respect to a square of term of that, and that series happens to be a convergent series. Then that kind of term sequence it will come in L2. For practical example, if I talk about 1 by n, 1 by n, it is a sequence. Okay, then so call it x is equal to 1 by n. So sequence, you can variety of way, there are various representation of sequence you can recall from math 1. So you can represent a sequence by 1 by n, or you can simply go to explicit, represent in this explicit form. So here n is coming from natural number. Okay, so you can go for explicit representation. That means what would be first term? First term would be 1 n equal to 1. Then second term would be 1 by 2. Third term would be what? 1 by 3. And fourth term would be 1 by 4. And likewise it will go on. So it is infinite. This sequence is having an infinite structure, and whether I will say that whether this sequence 1 by n it is in L2 or not. So in order to see that, what you do a squaring of every term of the sequence. So if you do a squaring, what would be term of nth term of the sequence? It is 1 by n. So if you do a squaring, it would be 1 by n square. And what is the convergence of this sequence? This sequence is always convergent. You can talk about convergence of the sequence from your calculus class. So this sequence is always 1 by n square is this series. Sorry, this series is always convergent. So it means this sequence 1 by n is in L2. It belongs to L2. Similarly, if you take another sequence minus 1 to the power n, this one is oscillatory kind of sequence, also decreasing. This also belongs to L2. It is a homework, you can verify. It also belongs to N2. Theory is same. So definitely L2 is very having a lot of sequence. So it defines an inner product. So here it is a linear space, we can define inner product. So what is the inner product? So inner product, what you do, just define inner product component wise. That means x, if you are taking two sequence, x is having x is first sequence having explicit form like this way, x naught x1 like this way, and y another sequence having explicit form, y naught y1, likewise it will go on. So do just component wise multiplication, and that component wise multiplication and sum it up, it will give inner product of between these two sequence x and y. So it defines an inner product in this L2. So we can say that L2 is an inner product space, and rest of property you can verify yourself. If you take another kind of subspace, a space, that one is talking about collection of all m by n matrices, then again it is also defining a inner product space. Then the question would be, what is the inner product here in Rm and m by n? So here it is a collection of matrices, m by n matrices. So inner product in this collection of matrices, we denote it by we define it by trace of A transpose B. So we are having if you take any two matrix A and B from this space of matrices and you define trace of A transpose B. What is trace? Trace is what? It is talking about sum of diagonal element. That means sum of diagonal element. Okay. Trace might be clear to everyone. Trace is talking about sum of diagonal element of the corresponding this matrix A transpose B. Sum of diagonal element. Okay. So in the space of matrices, you can define inner product as well like this way: diagonal elements, entries. Better, I would call it entries. Entries. Diagonal entries of the matrix. This underlying matrix A transpose B. A transpose B. Okay. That is that. And uh, this inner product is also I have already given picture of symmetric property of this inner product as well from the definition of the transpose of matrix. You can easily see all these structure. So definitely it is a very nice kind of inner product in Euclidean sorry in the space of matrices R m by n. So very apart from this inner product, you can define various other inner product in a space of all m by n matrix. Why? Because m by a space of all n by n matrix, it is just behaving like Euclidean space. It is just equivalent to Euclidean space R m into n. It is one time I had already discussed. It is very much a space of matrices is very much similar to a space of Euclidean vectors. So that is the concept. That's why we consider any image as a in matrix, black and white image as a matrix or gray image in matrix form. And we in MATLAB there is a command vectorization. So that matrix always it can be converted into vector form. So that concept is working very good in image processing and signal processing as well. So coming to norm and orthogonality concept in this inner product, so we will discuss in detail. So norm in a linear space, we had already seen norm in Euclidean space. So norm in an inner product space, how we define? So we will define with the help of so all these are property of norm. You just recall from Euclidean space. I am directly going to define a norm of the inner product. Norm in the inner product space. So if you're taking V is an inner product space, then norm in this inner product space we can define as a square root of inner product of f with itself. So always you can observe that this one is always a non-negative quantity. It would be always that means it is always a greater than equal to 0, and this inner product is this norm is always satisfying all these three properties. That means this property A and this positive definition property and this positive definition property, this subunity property and this triangle property. All these properties is satisfied by non-induced. That means that one is coming from inner product. And if you take any two vectors f and g, and when we will call these two vectors are orthogonal, if you find inner product of these two vector f and g, and that happens to be 0, then we say that f and g are orthogonal or perpendicular to each other. So it is just extension of orthogonality in Euclidean space. Okay. So the distance also we can define distance between if you take any two vector or any two function f and g, then we can always define distance by this way. With the help of norm, we can define distance between them. So all these are coming like this, that way. So also norm is giving one more concept that it is talking about energy. So if you take a square of norm, it defines energy. So you can observe that in a sound wave and also in wave structure, what you observe that all structure is so it is talking about vertical displacement, and this one is a particular wave. You observe a particular wave or okay. So what you do if you find the energy of this one, just do find a square of norm of the given wave or given function. So that will talk about the energy concept. So it is a physical meaning of that. Now, finding norm in a inner product space. How can you find? So few example I have taken it. So we are suppose we are taking a inner product space C01. What does it talk about? It is talking about collection of all continuous functions defined over the interval 0 and 1. Okay, 0 1. Then what is the inner product? So again, inner product is a very general inner product. So we define it by integral of product of ft over the interval 0, 1. Now we are taking a function t square, and question is find the norm of that function. So again, we will apply the definition of inner product norm with respect to inner product. So just define inner product. What would be? It would talk about a square root of uh, inner product of f with itself. So f is what? T square, and that means you are multiplying t square with itself. That means you are getting t square, t to the power 4, and you have to integrate over the interval 0, 1. Here it is mentioned. So if you after simplification of this integral, what value you are getting? You are getting a scalar number, square root of 1 by 5. This is the what? This is the norm of this given function in this vector space or linear space. Similarly, if you take another space C0 2 pi, that means it is collection of all continuous function over the interval 0 to 2 pi, and we again define inner product like this way: integral of product of these two function from 0 0 to, integral over 0 to 2 pi, and we take two function here sin t. In this interval we are taking two function, one function is sin t, another function is cosine t. Okay, now we do find the uh, inner product of f sin t with cosine t. What would be inner product? So simply inner product of sin t with cosine t would be integral from 0 to 2 pi of product of sin t and cosine t, and just do apply a trigonometrical identity. Sin t into cosine t, you can write in term of what? Sin 2t, 1 by 2 times sin 2t, and integrate what over 0 to 2 pi. What is the integral of this one? It is 0. So what does it say? That inner product of the sin t and cosine t is 0. It means that sin t and cosine t are perpendicular to each other. That is the criteria. So always sine wave and cosine wave happens to be perpendicular to each other point wise. Point wise. I'm talking about point